What if I told you that right now, you are surrounded by a hidden reality? A world where a single particle can be in two places at once, where connected objects can communicate instantly across the vastness of space, and where the very act of looking at something changes what you see. This isn't science fiction. It's the fundamental operating system of our universe, and we are on the verge of harnessing its power. Forget everything you think you know about computers, because today we are venturing beyond the world of ones and zeros. We are stepping into the weird, the wonderful, and the world-changing domain of the quantum realm. For the last century, our entire digital world has been built on a beautifully simple idea: the bit. A bit is like a light switch. It can be either on or off, a 1 or a 0. It's a world of certainty, of definite answers. Your phone, the internet, the supercomputers forecasting our weather. They all operate on this binary logic, performing billions of calculations a second by flipping these tiny switches. This classical approach has given us miracles, but it has its limits. There are mountains we cannot climb with this tool, problems so complex that even the fastest supercomputer on Earth would take longer than the age of the universe to solve. Imagine trying to navigate a maze with 1,000,000 possible paths. A classical computer would try each path, one by one, until it found the exit. It's methodical, it's reliable, but it's painfully slow. Now imagine you could explore every single path simultaneously. That is the promise of a quantum computer. It's a machine that doesn't just calculate, it explores a universe of possibilities all at once. It achieves this by using a new kind of bit, the qubit, which can be both 0 and 1 at the same time. And it harnesses one of the most baffling phenomena in all of physics: the mysterious, invisible link between distant particles. Today, we're going to peel back the layers of this revolution. We'll start with the heart of it all, the qubit. Then, we'll explore the mind-bending principles of superposition and entanglement, see how quantum algorithms are built, and even look at the incredible hardware and software bringing this future to life. This isn't just about faster computers, it's about a new way of thinking, a new lens through which to see the world. So, take a deep breath, and let's begin. To truly grasp the quantum leap we're about to take, let's solidify our understanding of the classical bit. Picture a coin lying flat on a table. It's definitive. It's either heads, which we can call 1, or it's tails, which we can call zeros. There is no in-between. Every piece of data in your life, every photo, every email, every song, is stored as a vast sequence of these definite heads or tails. A classical computer processes information by flipping these coins, one after another, at incredible speeds. It's a system built on certainty. Now, let's introduce the qubit, the quantum bit. Instead of a coin lying flat, I want you to imagine a coin that has been tossed into the air and is spinning, a shimmering blur of silver. Is it heads or tails? The answer is, it's both, and neither. It exists in a state of all possibilities at once, a blend of heads and tails. This is the essence of a qubit. It lives in a state of potential, a cloud of probability. It's only when we force it to give us an answer, when we measure it, which is like catching the coin, that it collapses into a definite state, either heads, 1, or tails, 0. This spinning coin state is called superposition, and it is the first pillar of quantum computing's immense power. While a classical bit is forced to choose, a qubit embraces ambiguity. It holds the probability of being a 0 and the probability of being a 1 simultaneously. This isn't a trick. It's a fundamental property of matter at the subatomic level. Electrons, photons, and atoms all obey these strange rules. By building computers from these quantum systems, we are not just creating a new kind of machine. We are learning to speak the universe's native language. Let's dive deeper into this idea of superposition, because it's where the magic truly begins. Think about finding a specific grain of sand on a vast beach. A classical computer would have to pick up and examine each grain of sand, one by one. If there are 1 billion grains, it might take 1 billion steps. It's a sequential, brute force process. A quantum computer, using qubits in superposition, approaches this problem in a fundamentally different way. It doesn't look at one grain at a time. Instead, it creates a wave of probability that covers the entire beach at once. Each qubit, being both 0 and 1, contributes to a massive superposition that represents every single grain of sand simultaneously. The quantum system doesn't check each possibility. In a way, it becomes all possibilities. This is the essence of quantum parallelism. It's not like having multiple processors working on a problem, which is how classical supercomputers gain speed. That's like having a team of people checking different sections of the beach. Quantum parallelism is like having a single, omniscient entity that can sense the entire beach in a single instant. It evaluates countless combinations, not by running through them, but by embodying them. This ability to exist in multiple states at once is what unlocks exponential speedups for certain types of problems. It allows a quantum machine to see the entire landscape of solutions at a glance, identifying patterns and relationships that would be forever hidden from a classical computer plodding along its single path. It's a shift from a linear, step-by-step logic to a holistic, probability-driven one. Now, if a single qubit is like one spinning coin, what happens when we add another? This is where our classical intuition completely breaks down, and the true, staggering power of quantum computing reveals itself. With classical bits, the growth is linear. One bit gives you one of two values, 0 or 1. 2 bits give you one of 4 possible combinations, 0, 0, 0, 1, 10, or 11. 10 bits give you 1,024 combinations. It's a respectable growth, but it's additive. With qubits, the growth is exponential. One qubit, as we know, holds 2 states in superposition. But when you have 2 qubits, they can hold all 4 of those combinations, 0, 0, 0, 1, 10, and 11 in superposition at the same time. Add a third qubit, and you can represent 8 states simultaneously. With just 10 qubits, you can hold all 1,024 possible combinations in a single quantum state. By the time you get to 300 qubits, the number of states you can represent simultaneously is greater than the number of atoms in the known universe. Let that sink in. A 300-qubit quantum computer could, in a single operation, process a dataset larger than the physical universe itself. This is why you hear so much excitement and hype. We're not just talking about a computer that's a little bit faster. We are talking about a machine that can access a computational space of unimaginable size, while a classical computer holds a single value at a time, a single point in that vast space. A quantum computer creates a superposition that encompasses the entire universe of potential outcomes. This isn't just an upgrade, it's a phase change in the nature of computation itself. If superposition is the first pillar of quantum power, entanglement is the second, and it's arguably the weirder of the two. It's a phenomenon so counterintuitive that Albert Einstein famously called it spooky action at a distance. Imagine you have 2 of our spinning coins, our qubits. Through a special process, we can entangle them. From this moment on, they are no longer 2 independent coins. They are a single, interconnected system, even if we separate them by billions of miles. They are linked by an invisible, unbreakable bond. Here's the spooky part. If you now catch one of the coins, measure it, and find that it landed on heads, you will instantly know, with 100% certainty, that the other coin, no matter how far away, has just landed on tails. It's as if the first coin communicated its state to the second one faster than the speed of light. This isn't communication in the classical sense. No signal is sent. It's a fundamental property of their shared quantum state. Their fates are intertwined. In a quantum computer, entanglement is the secret sauce that allows qubits to work together in perfect harmony. While superposition lets each qubit explore many states, entanglement coordinates their explorations. It creates complex, system-wide correlations that classical bits could never achieve. If qubits were a choir, superposition would allow each singer to sing every possible note at once. Entanglement would be the conductor, ensuring that all those probabilistic notes combine into a single, coherent, and powerful harmony. It's this coordination, this hidden connection that turns a collection of individual quantum parts into a computational powerhouse greater than the sum of its components. When you combine superposition and entanglement, you get something truly extraordinary, a new form of computation based on the principle of interference. This is the secret to how a quantum computer sifts through that universe of possible answers to find the right one. Think of it like waves in a pond. When two wave crests meet, they reinforce each other, creating a bigger wave. This is called constructive interference. When a crest meets a trough, they cancel each other out, leaving the water flat. This is destructive interference. A quantum algorithm is a carefully choreographed sequence of operations designed to manipulate this interference. It starts by putting the qubits into a massive superposition, representing all possible solutions to a problem at once. This is like creating ripples that spread out across the entire pond. Then, through a series of quantum operations, the algorithm skillfully uses entanglement to guide how these probability waves interact. The waves corresponding to the wrong answers are guided to interfere destructively. They cancel each other out. Simultaneously, the waves corresponding to the correct answer are guided to interfere constructively. They amplify each other. At the end of the computation, when you finally measure the qubits, the probability of them collapsing into the wrong answer has been reduced to almost zero, while the probability of them collapsing into the right answer has been amplified to nearly 100%. The result is a system that doesn't find the answer by checking every box. It finds it by making the wrong answers disappear and the right one shine through. It's a powerful, probability-driven search engine that can solve certain complex problems far beyond the reach of any classical machine. All of this talk of probabilities and waves can feel very abstract. So, how do physicists and engineers actually visualize and work with a qubit? They use a beautiful and elegant tool called the Bloch sphere. Imagine a globe. For a classical bit, its world is very simple. It can only exist at 2 points. The North Pole, representing 1, or the South Pole, representing 0. That's it. Its entire existence is confined to these two opposite points. A qubit, however, can exist anywhere on the surface of this globe. A point on the sphere doesn't just represent 0 or 1. It represents the specific mix of probabilities of being 0 or 1. If the qubit's state is pointing directly at the North Pole, it's a definite 1. At the South Pole, it's a definite 0. But if it's at the equator, it's in a perfect 50-50 superposition of both. A point in the northern hemisphere means it's more likely to be a 1 when measured, and a point in the southern hemisphere means it's more likely to be a 0. The Bloch sphere gives us a map of a qubit's state. It turns the abstract math of quantum mechanics into something we can visualize. And most importantly, it gives us a way to picture what happens when we perform an operation on a qubit. The quantum gates we'll talk about next are the tools that allow us to move the qubit's state around this globe, carefully rotating its vector to point in precisely the direction we need for our algorithm to work. It's a geometric representation of quantum computation. If a quantum algorithm is the overall strategy, quantum gates are the individual tactical moves. Just like classical computers have logic gates, like AND, OR, and NOT, that manipulate bits, quantum computers have quantum gates that manipulate qubits. But there's a crucial difference. Classical gates take in definite inputs and produce definite outputs. A NOT gate simply flips a 0 to a 1. Quantum gates, on the other hand, perform rotations on the Bloch sphere. They are the choreographers that guide the dance of probabilities. Let's look at a couple of famous examples. The X gate is the quantum equivalent of a classical NOT gate. It performs a 180-degree rotation of the qubit's state around the x-axis of the Bloch sphere. If your qubit starts at the South Pole, Mo or Vuro, an X gate will flip it perfectly to the North Pole, 1. But then you have gates with no classical counterpart, like the Hadamard gate. This is one of the most important gates in quantum computing. Applying a Hadamard gate to a qubit at the South Pole, Mo or Vuro, rotates it exactly to the equator. It takes a definite state and puts it into a perfect 50-50 superposition of 0 and 1. It is the gate that kicks off the quantum parallelism the one that spins the coin. A quantum circuit is created by stacking these gates in a sequence. Each gate performs a specific rotation, a precise twist or turn of the qubit's state on the block sphere. A full algorithm might be a long and complex sequence of these gates, a dance routine for probabilities, designed to move the qubits from their initial state to a final state where the answer to our problem can be read. It's a language of control, written in rotations and interference. Now that we have the building blocks, qubits, superposition, entanglement, and gates, we can start to appreciate the genius of quantum algorithms. These aren't just classical algorithms run on a faster machine. They are entirely new ways of thinking, designed from the ground up to exploit the strange logic of the quantum world. One of the most famous examples is Grover's algorithm. Imagine you have an unsorted database, a massive phone book with 1 billion names, but they're not in alphabetical order. You're looking for one specific phone number. Classically, you have no choice but to start at the beginning and check every entry until you find it. On average, you'd have to check 500 million entries. Grover's algorithm transforms this. By using superposition to represent all the phone numbers at once and interference to amplify the correct one, it can find the number in roughly the square root of the number of steps. For 1 billion entries, that's the difference between 500 million checks and about 32,000 checks. It's a dramatic speed up for search tasks. Even more world-changing is Shor's algorithm. This algorithm is designed to do one thing exceptionally well: find the prime factors of a very large number. This might sound like an obscure mathematical puzzle, but it is the bedrock of modern cryptography. The security of your online banking, your emails, and virtually all secure communication on the internet relies on the fact that it is incredibly difficult for classical computers to factor large numbers. Shor's algorithm can do it exponentially faster. A problem that would take a classical supercomputer billions of years could be solved by a large-scale quantum computer in hours or minutes. This single algorithm has the potential to break most of the cryptography we rely on today, which is why scientists are already working on new, quantum-resistant forms of encryption. These algorithms are the proof that quantum computing isn't just a theoretical curiosity. It's a technology with profound, real-world implications. The concepts we've discussed are incredibly deep and, let's be honest, can be mind-bendingly complex. Trying to learn this on your own can feel like drinking from a fire hose of academic papers and dense mathematics. This is where modern tools can revolutionize the learning process itself. To help put this script together, I imagined using a next-generation AI platform. Let's call it MGX Deep Research. Think of MGX not as a single AI chatbot, but as a collaborative team of specialized AI agents. You give it a high-level goal, like explain quantum computing to a curious audience. One agent, the researcher, would scour scientific papers, textbooks, and articles to gather the core information. Another agent, the synthesizer, would take that raw data and organize it into a logical narrative structure, just like the one we're following today. A visualizer agent would suggest analogies, like the spinning coin or the block sphere, to make abstract concepts concrete, and a coder agent could even generate working code for simulations. Unlike single-agent tools that give you a flat answer, MGX's collaborative system is designed for multi-step, deep-dive projects. It can generate structured reports, suggest visualizations, and even help build functional prototypes. It's a tool that doesn't just give you information, it helps you build understanding. It accelerates the journey from curiosity to comprehension, turning the daunting task of research into a creative and collaborative process. It's an approach that mirrors the very synergy we see in quantum systems. Multiple agents working together to produce a result far greater than anyone could alone. Let's make this concrete. Imagine we tasked MGX with a specific project. Build an interactive web application that lets users visualize the effect of quantum gates on a qubit. This is where the platform would truly shine, bridging the gap between abstract theory and hands-on experience. The MGX system would first generate a project plan. The coder agent would write the front-end code for the user interface, a 3D model of the block sphere, and buttons for the X gate and Hadamard gate. Simultaneously, the synthesizer agent would write the explanatory text to appear alongside the visualizer, explaining what each gate does. The researcher agent would provide the precise mathematical matrices needed to calculate the rotations on the sphere. Within minutes, MGX could produce a working prototype. A user could open this app, see a qubit starting at the Lambeau state, the South Pole, click the Hadamard button, and watch in real time as the state vector rotates up to the equator, instantly seeing the probability chart next to it shift to a 50-50 balance. Then, they could click the X button and watch it flip 180 degrees. This is how you turn passive learning into active exploration. By using a tool like MGX, we can transform a dense, theoretical subject like quantum mechanics into an interactive playground. It demonstrates how advanced AI can serve as an accelerator for human understanding and innovation, allowing us to build tangible learning tools that make the invisible world of quantum computing visible to everyone. An interactive tool like our qubit visualizer needs a robust and scalable backend to support it, especially if it were to be used by millions of people. For our hypothetical MGX platform, this foundation is provided by a system we'll call Superbase. This part of the story highlights a crucial, often overlooked aspect of any technological revolution: the incredible engineering required behind the scenes. In a recent, fictional talk, the creators of Superbase explained their architecture. Their platform is designed to handle millions of individual PostgreSQL databases, ensuring that every user's project is isolated and secure. The data itself isn't stored on the same servers that run the computations. Instead, it uses a system like Amazon S3 for storage. This is a key design choice we'll come back to. Most impressively, they built a powerful multi-orchestrator called Multigrass. Imagine you have thousands of servers running these databases. What happens if one of them fails? Multigrass automatically detects the failure and, in real time, promotes a replica to take its place, ensuring zero downtime for the user. This failover system is incredibly difficult to get right. It has to ensure that all servers agree on which one is in charge, a classic problem in distributed computing. This back-end infrastructure, with its focus on resilience, data safety, and seamless scaling, is what allows a powerful tool like MGX to exist. It is a lesson that applies just as much to cloud computing as it will to the future quantum internet. The most exciting applications are only possible when built on a foundation of brilliant, reliable engineering. Let's distill two profound technical lessons from this back-end architecture because they connect beautifully to the challenges of building complex systems, including quantum computers themselves. First is solving the consensus problem for automatic failover. This is one of the hardest challenges in distributed computing. Getting a group of computers to agree on a single source of truth, especially when some of them might fail or send conflicting messages, is incredibly complex. The engineers at Superbase solved this to ensure their system is resilient. This quest for consensus and reliability is mirrored in the field of quantum error correction. Individual qubits are incredibly fragile and prone to decoherence, or losing their quantum state due to noise from the environment. Building a reliable quantum computer requires creating systems where many physical qubits work together to form a single, stable, logical qubit that can correct for errors, maintaining consensus on the correct quantum state. Second is the principle of decoupling storage and compute. By separating where data lives, S3 storage, from where it's processed, the database servers, Superbase gains immense scalability and reliability. You can scale your processing power up or down without affecting the underlying data. And if a compute server fails, the data remains safe and can be instantly attached to a new server. This architectural wisdom, separating components to increase flexibility and resilience, is a core principle of good engineering everywhere. It is what underpins the stability of MGX and connects the most modern cloud infrastructure with the foundational challenges of building the quantum machines of tomorrow. Strong systems are built from smart, decoupled parts. We have journeyed from the spinning coin of a single qubit to the cosmic symphony of a full quantum algorithm. We've seen how superposition and entanglement create a computational power unlike anything that has come before. We've explored the elegant geometry of the block sphere and the choreographic precision of quantum gates. And we've seen how modern AI and engineering principles are not only helping us build these future machines, but are also making it possible for all of us to understand them. Quantum computing, though still in its early days, is no longer a distant dream. It is an emerging reality that is already beginning to reshape our world. From designing new medicines and materials at the molecular level, to optimizing global financial systems and creating unbreakable codes, the potential applications are staggering. The road ahead is long and filled with challenges, from building more stable qubits to developing new, powerful algorithms. But the journey is well underway. In our next video, we will dive even deeper, exploring the flagship algorithms like Shor's and Grover's in full detail, unpacking the step-by-step logic that gives them their power. We are standing at the edge of a new technological frontier, one built on the strange, beautiful, and deeply fundamental logic of the quantum world. The greatest lesson quantum mechanics teaches us is that reality is often far more subtle and interconnected than it appears. It encourages us to embrace uncertainty, to see the power in possibility, and to recognize the hidden connections that bind everything together. The advice from this story is simple. Stay curious. Approach the complex problems in your own life not always with a linear, brute force mindset, but by stepping back to see the entire landscape of possibilities. Sometimes, the most powerful solutions come not from trying every path, but from seeing how they all relate to one another. So, I have to ask, what part of this quantum journey fascinated you the most? And what problem in the world would you want to solve if you had a quantum computer at your fingertips? Let me know in the comments below. Thank you for joining me on this incredible exploration. I wish you all the very best of health and a future filled with discovery. Don't forget to subscribe to the channel for our next deep dive into the quantum horizon. Stay curious, and I'll see you next time.